Any questions about the homework? Okay. Any questions about the project? So the project proposals are due, what you call it, on Tuesday. I haven't spoken to that many teams yet about what they're doing. Are there any questions generically about projects? Okay. A quiet bunch today. Okay, maybe I will give you another crack at this a little bit later. But what I'd like to talk about today a little bit is some issues about building models. Again, you guys are for your homework and for your projects, many of you will be building models. And I wanted to talk today about kind of philosophical questions about sort of what's involved in building models. Again, when we think about what, kind of data science is, I think of it as, something where you want to analyze data to get a question and, to answer some kind of a question. Here was a graphic I kind of showed that suggested what basically, in general, one's interested in. There's some subject you're curious about. There is some subject you have data or want to find data to analyze it. There's some level of exploring the data, visualizing it and plotting it and stuff like that, that actually is also sort of involved in when you want to communicate the results. The phase of the pipeline that we haven't really talked about so much is modeling. How do we build a some kind of a fit, some kind of a predictive model out of what we see in the data set? So one thing that should be clear by now, after you've done your first, your homework assignments, is that there are many possible fits that you can have, many possible models you can have to try to predict what a data set is. This is a cartoon I stole from someplace. Which is this place? Is this Exceed? Any of you who know about comic strips?
Yeah, this is XKCD.
Exceed. Okay, this is a fun XC. What is it? ED? Is that what it is? So this is a good web comic. In case any of you haven't seen it, this is kind of XKED. Excuse me. Gets sort of at the graduate student-like experience or the scientist-like experience, and says interesting things for being funny. And of course, what this one says is it gives you the same data set, and they're showing you 20 different kind of ways to look at the data to try to make it say something. And of course, all 12 different ways, and all 12 ways say something different, okay? And so, actually, which one do you like? If you look at this data, which fit do people like, okay? Now we're looking at many different kinds of fits. There's a linear fit to the data. There was a quadratic fit to the data. There was a logarithmic, fitting it as a logarithmic function, which again goes slower as n gets larger. An exponential fit, which grows more rapidly as n gets larger. And some more complicated, I will argue, sort of piecewise fits, okay? Things like LOES, things like connecting the lines or some kind of an ad hoc filter. Okay, which ones of these do people, and in this case, some kind of explicitly piecewise thing, claiming there's two different regimes. Which one of these fits do you guys like best? Is there anybody who has an opinion here? It should be clear that you can draw surprisingly convincing plots, okay, on the same data set that yield completely different conclusions. And so to a certain extent, in order to find a good fit for this thing, we do need to have some kind of a philosophy of modeling that we're going to be working with. And that's kind of what I really want to kind of talk about now, are a few different kind of philosophies of how you go about building a model. And, you know, I think that it's important to keep a bunch of different philosophies in mind with what you're doing. So, you know, it gives you some kind of a way to think about things, okay? And the first model philosophy that I'd say that one hears a lot is Occam's razor, okay? How many people have heard of Occam's razor? And actually, don't be afraid to turn on cameras. It'd be nice to see some people. What is Occam's razor? How many people, who's heard of Occam's razor, and what does Occam's razor mean? Okay, somebody.
Means the simplest solution is usually the best one.
That's kind of simplest solution is best is kind of the you know, the story. When we're talking about Occam's razor, razor is not being used as a way to remove hair from his face. Okay, it was kind of an old-fashioned word, kind of about a reasoning principle to separate one thing from another. Occam was a priest, you know, if I remember, some kind of clerical figure in like the 11th century, and his theory was that you know, and the question was, if you wanted to explain something, resorting to, you know, God made it like this, is kind of a pretty complicated explanation. If you could say that, you know, if you could come up with a simpler explanation, that's probably the more likely to be right. So where does Occam's razor come in the kind of modeling that we do? Okay, well, one thing, if you have a model with 100 parameters, okay, and it yields a certain performance, and another model with 10 parameters yields almost the same or almost the same performance, which one should we like better? Occam would tell you that he likes the simpler model, the one with the fewer parameters. Okay, it's probably more robust. It's probably getting at the better at the explanation of why is this thing happening. Okay, so what do you think Occam would have felt about deep learning? Think Occam would like deep learning or not like deep learning?
Not at all.
What?
Not at all.
You don't think he'd be a fan? Why wouldn't he be a fan? Okay. Typically, these models have millions or, you know, thousands or millions or billions of parameters in them, right? So what I would say is that certainly if you have two models, one of which is, you know, much simpler, okay, and yields the same performance or very similar performance, Occam would certainly be in favor of that. Okay, I have occasionally had students in the past. I remember one student I talked to was trying to impress me. He said, oh, I was working for a company and we were, you know, trying to identify whether chips were bad. Okay, I think he had software and you know, they had, we built a model and I used deep learning and I got 90% accuracy. And I said, that's great. How'd they do it before? Well, they had this model where they just, you know, looked to see how many parts were bad. And how accurate was that? Well, they said it was 90% accuracy. So, of course, the deep learning thing in that case would have been rejected. On the other hand, you know, if you do have better performance, Occam would presumably be impressed by that. So the simplest explanation is best, but the quality of how good the explanation is also would kind of matter. Now, we will be talking pretty soon about, you know, talk more deeply about linear regression and other methods, which I imagine some of you are using in your model. You know, there are techniques in machine learning, okay, that they will talk about like LASSO regression or ridge regression, where they add a penalty function to try to reduce the number of variables that are actually being used. Maybe you try to fit a curve with 100 data points. But if you use a LASSO or a ridge regression, maybe the model will decide, well, you know, I'd rather have a less optimally fitting thing if it used less variables. Okay, and so you know, using techniques like this, you're kind of thinking like Occam. Any questions? Any questions of why Occam's razor is a good idea? Another issue or way of thinking about modeling that that people you hear a lot is people talk about bias variance trade-offs when they're building a model. Now, what is bias? The bias of a model. When you are developing a model, okay, the bias is kind of what you come into. You know, when bias is kind of a bad word when we think about it in social contexts where, oh, you know, you're biased against a certain kind of people. That's obviously a bad thing. But what does that mean when you're talking? You're kind of coming in with a preconception that some group of people are bad, okay? When you go to a modeling problem, you're often coming in with some kind of a bias, okay? Now, when you use linear regression, are you making any kind of a biased statement about what the right relationship is? Okay, even before you do any fitting. Inherently, if you're using linear regression, you're saying there's a linear relationship between these variables that will explain what's going on, okay? And the bias is kind of the limitations in the space of models that you will consider, okay, in order to with what you're choosing to do, okay. So that's what kind of bias is. What you come in with the models, okay. Obviously, what you call deep learning models probably are very unbiased in some ways because you know they'll kind of allow all kinds of different fits, okay. On the other hand, variance is the problem that when you basically have how sensitive the model is to small changes in the training set, okay. If you do a linear regression with a large amount of data, no point is going to contribute very much to the coefficients of the model, okay. So there's relatively little variance. On the other hand, if you have a very high parameter model, especially relative to the number of training examples, depending upon each training example is going to contribute something to the model, okay? And there is a danger of, you know, overfitting. So another way that I think about it is bias, and the bias variance trade-off is the risk of underfitting, okay, your data by basically picking too simple a model, or, you know, or fundamentally the wrong model, versus variance, which is that you're overfitting the data. Any questions? Okay, it should be clear that you should be thinking about what these issues are on your data set. Again, for you guys, you've got a, you know, what you guys are going to be trying to build models. How many training examples do you have for the for the homework 3, for example?
3,000.
How
3,000.
many?
3,000.
A few thousand, okay. And how many dimensions are you using to try to predict this thing, okay? Something like when you're, depending upon what, you know, recognize that there is a few thousand points is good, but not an unbelievably large amount of data. The question of, and again, this is not to get you nervous about your homework, so I'm just trying, don't get nervous about that. But recognize that, you know, these are the kind of things one should think about. Any questions? Now, one favorite quote I had about modeling okay, that you see in, I think, almost any data science thing, is that all models are wrong, but some of them are useful, okay? And that's kind of, I think, an important lesson to come away with. When I think about models, okay, we're going to talk a little bit later about what I'll call first principle models that kind of assume the way the world works, okay? If you think about, you know, like gravitational forces, Newton had this model that he figured out of, what was it? That something like the force of gravity was something like, correct me if I'm wrong, something like G times M1, M2 over D squared. Is that right? Does anyone remember the force of gravity
It's
type of
over R square,
It's,
where R is, yeah.
yeah,
over
it's
R square.
I'm right. Oh, that's pretty amazing. Okay. But if you think about it, you know, what did Newton do? Newton came up with a first principle argument that said that the force due to gravitation is gonna look like this. Okay. And then it was simply a data fitting problem. He then had to do linear regression or whatever he wanted to try to figure out what that constant G was, right? So in a first principle model, you come in with a lot of bias. In a data-driven model, okay, you come in assuming nothing, but you're at risk of overfitting. Any questions about bias variance trade-offs? Okay, good. The one book that I find very appealing on modeling, which again, I don't want you to read now because you guys are busy, but at the end of the semester when you're looking for something to read, I do like this book by Nate Silver, which is kind of a, Nate Silver is a kind of public figure who made his, you know, who got famous as an election forecaster. And so I'm spending a lot more time with Nate Silver these days than I should, at least his website. You know, he has thought, you know, he's not actually an academic, but he is someone. He worked at a hedge fund. He has done a fair amount of data science work in different areas. And, you know, the question of how would he go about doing models? Again, this is from when Romney, you know, in the 2012 election, this was kind of you know, prediction by his site. He would try to predict for every state what was the probability of it going for Democrat or Republican, and from this would build some kind of forecasting. So in his book, he just outlined a couple of different philosophies of modeling that I think are useful ways to think about things, okay? And so let's try to talk about it. He likes to think, and he says, it's important when you're building a model to think about things probabilistically, okay? It's important to think about things in, you know, in a world where recognizing that you're going to be, you know, your forecast should change when you get new information, okay? And typically when you're trying to make a prediction or a model of something, okay, there's going to be new information coming in. It's important that your forecast respond to it. He recommends looking at a lot of different models and trying to get a consensus of them. Okay, so that would be one approach that he would use for making a forecast. Linear regression is a technique. Okay, you can imagine making different models with different assumptions. Okay, and seeing how that, to what extent they agree or don't agree. Okay, and finally, he believes in using Bayes' theorem, you know, as sort of a good technique to update forecasts in response to new information. So let's look at these kind of things. The first thing is that, you know, getting a single answer of a prediction, okay, from a, what you call it, a model is not really what you would kind of like. Now, for you guys, when you're using, I gather many of you are using linear regression, okay, to try to forecast the gross of a movie. Is the output of that forecast a number or a probability distribution?
It's a number.
A number, okay? So what you call it? Nate Silver wouldn't be quite so impressed by that. Again, it's what you asked. It doesn't mean linear regression's a bad thing. But recognize that if you wanted to say what is the probability of there being a gross of a movie, if you're using linear regression, what is your probability distribution looking like? Whammo. Okay, you are saying that there is one value, and that is what the gross of the movie is going to be. Okay. In principle, a better model would be one that had some level of probability associated with it. Okay. What might be a way that you could get a probability distribution out of such a model? The people see what the problem kind of is. According to your prediction, you're going to say that there's a 100% chance that the movie is going to gross $71 million. There's no chance of it grossing $70 million. Is there any way to turn a forecast like that into a probabilistic kind of thing?
Could you just use the variance from the initial input data and just say it's going to be plus or minus the single number you get?
So one possibility would be that you might want to think, if your predictions are reasonable, perhaps there is a distribution of the errors associated with the prediction, right? So it's not probably unreasonable to know something about if you knew something about a standard deviation or the distribution of error your model is likely to predict, then this is a much better interpretation of this, right? Does everybody kind of see it? Even with a linear regression, there would be a way of turning this thing into a probability distribution based on some kind of an error model of what you're likely to have. Okay, so this is the kind of thing that if I was going to be trying to present a forecast to somebody, okay, that would be one way that I would be thinking about it. Okay, any questions about it? And some other models that we will see, okay, present more naturally probability distributions. One type of model that Nate Silver uses to predict the election, he uses simulation-based models where he's going to kind of, try to predict certain, knowing that the polls he's using has certain amount of error, figuring out what's the consequences of certain errors in the polls. And he will adjust the numbers and run simulations and tell you what fraction of the time will you get above a threshold, will one candidate win, okay? So there are other models that do kind of produce probability distributions. And this seems like something you should be thinking about if you're doing a serious modeling. Any question about that? Now, one thing to note is that when you have a model, okay, knowing what its accuracy is, what the range of what predictions that you're kind of making, okay, is kind of important to know. And, again, a good model will have more accuracy than a bad model. But note that even, what a good model is depends upon the problem. If you could, predict whether the stock market will go up tomorrow with a probability just slightly greater than a half, that would be enough to be rich, okay? Or to win at football. You could predict the football winners at 55% against the spread. You would be a winner. Okay. Any questions about that? So that's one thing that we need to think of, thinking about probabilistically about models. And again, we talked about probability. Probabilities have these kind of properties we talk about, that over a distribution they sum to 1. Okay, no probability is negative. And, rare events, do not get probabilities of 0. Okay. And again, one way to think about probabilities are that they are kind of measures of the complexity of uncertainty and humility, which is kind of important to have in a model. Any questions? I think that you believe. And, you know, recognizing that one way that we get probabilities out of models was with logistic regression, with the logit function, that it's possible to turn scores into probabilities in a sensible way. Okay, so there are techniques for reasoning about things probabilistically, and I want you to think about that. Any questions?
Yeah, could we back up quickly? Which definition for logit are we using here? Because there's a lot of them.
Well, there are a lot of logit functions. Again, what were logit functions we talked about? And we will talk about it again when we talk about logistic regression. We wanted a function that mapped a score function. Okay, X, let's say, was some kind of a score of how good or bad something was. Okay, and we wanted to map it to a probability. The logit function had the property that when the score was 0, it was a half. As X got bigger, as X approached, got more and more positive, the logit got closer to 1. So the probability of, you know, let's say, you know, one guy winning, if you had a score that was kind of going to reflect that, the higher the score, the closer that probability came to 1. And it approached 0 as you know, as X went to minus infinity. So this was the logit function. And when you say there's many different logit functions, I think this is the logit function. Sometimes there is what you see here is some constant to represent how much does it tweak.
I was more so talking, this was the answer to the question I meant to ask, which was the definition, not of the function, but of the term, because in deep or machine learning, they just use logic for so many different things. So I wanted some clarity on
logit, as far as I'm concerned, is a function that's kind of mapping things to probabilities that has this kind of shape to it. I think this is pretty consistent for what logit usually means, this function. Or so, you know, any questions? Okay. One thing that makes that I find is really good when it comes to modeling, an important thing is, I think, about trying to keep your model alive. Okay, that typically models are you know in somewhat of a dynamic environment. Okay, and that if you have, you know, quite often in many applications, you know, you're kind of making you know, forecasts change over time. If you want to think who's going to win the election, okay, if you want to make some kind of a prediction, I think a good model should have the following property. One is, as you get closer to the event, it converges on the right answer. Okay. The model, should, okay, display its old forecasts, so you can judge how consistent the results are. Okay. And it's important to kind of retrain on the fresh data when you get it. One problem in the world that happens a lot is that models tend to get trained. What might happen in industry? You train a model, okay? You put that model into practice, and then you keep using it over time, even though the world changes. And I'll show you a danger of that. This was Nate Silver's forecast at the time I had class 4 years ago, okay? When it was predicting the Trump versus Clinton election. And on this day, actually, the the probability of Clinton winning the presidency is almost exactly the probability that Biden has of winning the presidency this year. Okay. Now, what do we think? What do we notice when we look at this forecast, though, about the election? This shows his predictions over the previous 3 or 4 months. What do you notice about this? If you look at this, obviously you know how the story ends. Okay, One way to read this would say, wow, that's 86%. I got to feel pretty confident about this. Okay? What's another way to read this?
There's a lot of fluctuation in the previous
variance
months.
in the forecast is extremely large. This was quite a volatile election. And what actually happened? You know, probably a day or two after this slide was put out, there was a big news event that suddenly shifted momentum Trump's way. Okay? And, you know, if you looked at the forecast from then on, the forecast, the election, it probably ended up looking like this. Was what you call it? What the final model ended up looking like. When I was talking this to people, you know, about the results of the the election model in my data science class that year, one student showed me about this time an article that was very angry at these election forecasters. What do you mean they only think it's going to be an 86% chance that Clinton was going to win? It should have been 99%. This is obvious. They're just trying to make this closer race than it seemed. Okay? But anyone who looked at the variance of these forecasts, okay, should not have been as confident as a number like that would show, right? What is, by contrast, what does the curve look like this year? If I take a look at it, I think it would be probably fair to say that that if you had looked at his forecast so far, it would probably look something like this. It has been a much more stable race than it had been last time. So this is why I feel a little bit better about the outcome than I did then. But you know, or a little more certain I know what the outcome is going to be. But it's still, you know, it's still a forecast. Any questions about that? Okay, so seeing how your forecast is changing over time seems to be an important thing to knowing about how volatile it is. Any question? So when I'm trying to, you know, when in trying to understand who's going to win the election or something like that, you would like to try to look at as many competing forecasts as you can. Okay, so you know, if you have many different models that people are using, and they're all really different and they're all saying the same thing, that is better than one guy with a model. If your model is saying something different than other people, it could be that you're smarter. Doesn't mean you're necessarily wrong, but it does mean you have to be a little bit more humble. So what, for example, might be competing methodologies for predicting who's going to win the presidency? One thing is that there are betting markets where people can bet on the candidates. Okay, and I haven't looked or I haven't heard as much about them this year. But it'd be interesting to know what odds they're giving on this is people with their own money and their own gut. Okay, if the prediction markets are saying about the same thing as Nate Silver's model, I feel better about Nate Silver's model. Okay, if you have other people who are doing other models, okay, you feel better about that. That's one way to think about it. Another thing is to think about what really simple models are saying. So if you have a very complicated model that is making a prediction and the answers are wildly different than simple baseline models, which I'll talk about in a minute, okay? That is a sign of, you know, it could be that your more sophisticated model is smarter, or it could be you're making it too complicated. Likewise, having multiple different ways of trying to make the forecast, okay, gives you a better idea. How many of you have heard of the machine learning technique called boosting? Okay. Boosting is a technique, which I hope we will get a chance to talk about, where if you have a bunch of different classifiers to try to make a prediction, okay, who's going to win the election, How do you combine all these weak classifiers into a stronger result? Okay. And again, that's kind of an approach that if you think about it, is working by looking in some sense for a consensus from different classifiers. Okay. Any questions about that? So this is one thing I would like to see done. One other example of why live models are good and paying attention to live models is the story of Google's flu trends. You know, starting around 2008, this guy at Google had this great idea and said, you know, a lot of people are, flu, the number of people who die of flu in the United States every year is a large number, okay? And there, you know, we have an even worse problem now with COVID, but an important thing that the Center for Disease Control does is try to monitor how much flu there is in the United States to see if there's an epidemic going on. And one of the ways that the way the CDC worked basically was they would talk to doctors. How many flu patients are you seeing? They would go and look at how many people are buying certain kinds of drugs to try to make a forecast. And so the CDC produces a very accurate but somewhat slow measure of how much flu there is in the United States. The Google people said, wait a second, wouldn't it be faster if we monitored search queries, okay? And tried to predict if people are typing in, flu, that probably means that if people start typing in flu more, if people start typing in, I have a headache, okay? If people start typing in, sneezing, how do I cure sneezing? What's good for sneezing? You could imagine that there would be a certain number of queries that people would make that would be more likely to be made if there was flu going around. And so they fitted a model to the CDC data, okay, to try to predict what the amount of flu in the United States was. And by training on past data and comparing it to the CDC thing, they were able to come up with a pretty accurate model. It looks like it did something weird here. I don't quite know what happened there. Okay, actually it happened, it was a bad model. It diverged and they stopped it. That's what this kind of shows. Then they refit their model. And as you look, it kind of really did a pretty good job predicting until at one point, Google went crazy and started declaring, my God, there's going to be an epidemic. There's going to be a terrible thing. And, it was off by a factor of 2. Okay, what happened with the Google flu model? Well, there was a very interesting paper in Science where people tried to diagnose what ended up happening. Well, one problem was that they fit the model and they let it work and they basically just let it run. And they didn't retrain the model over time. And what happened? Well, one thing that happened was Google added search suggestions. Okay, a lot of things change in the world over time. At one point, if you typed in, flu, it might come back. Are you interested in sneezing? Are you interested in remedies for flu? And people started making more queries once they had done it. When the conditions of the world changed, the frequencies of these signals changed. And the model started diverging more and more from the observed data until finally it got to be a disastrous prediction. Okay, so this is kind of the importance of having a model that retrains over time, okay, that recalibrates itself, because presumably there's conditions in the world that change, okay? Any questions about that, or Google flu, or any of these kinds of things? So these kind of search-based models, query models, are actually quite interesting. But again, they have to be recalibrated. They require, require some care and handling. Okay, when I think about building models, I think about two different kinds of things. One, there are, like I say, what I will call first principle models. These are the ones where I have an explanation, a theory of the world that describes why something is happening. Okay, and and they will make predictions based on this theory of the world. In fact, some of you, I don't know if you know, there's a fellow in the political science department at Stony Brook who has every 4 years has made a prediction of who's going to win the election. And his prediction is based on only 3 things. Okay, if I remember correct, it's based on something like the unemployment rate. There is how long has the party been in power? And one other factor that has nothing to do with the unemployment rate, the party in power, and let us just say maybe the stock market. Let's say maybe the inflation rate. I don't know what it is. But you could imagine he'd have a theory that says when unemployment is high, people get angry and they vote against the current president. When a party has been in there too long, people get grumpy and they'll vote against them if they've been in power too long. And when inflation is too high, people are unhappy and they're going to vote against them. This, if you think about it, was a first principle model. He has an idea of how the world works, and he was able to show that, that over the last 20 or 30 elections that had been held in the United States, this simple formula would predict the winner, 90% of the time. And in the last election, he said he was the only one saying Trump was going to win. Okay. And in that case, he was right. I think he's still saying Trump's going to win this one. Okay. But again, this is a first principle model. There's a view of how the world should work, and you do that. A data-driven model, on the other hand, is based on observed correlations between parameters. And, this is where the machine learning comes in. And I would argue that in general, good models are probably some mixture of both. Adding more factors to a model that are just kind of things you have data for, but probably, no reason to believe they're relevant, probably don't make the model better. Okay. So let's think about these things. Again, for you guys on your homework, you're predicting movie gross. Can anyone come up with a principled model? Let's say, not data-driven model, but a principled model to describe why, what a movie should gross, based on an understanding of the world. What would be an example of a principled model, first principle model?
The one with higher popularity should gross more.
You're saying that the more the popularity is, the more gross it should be?
Yeah.
That's a theory of the world. So if you had a measure of popularity, you could translate that to, I guess that's a theory of the world. One that I would say as a principled word, again, it depends what your theory of the world is. My theory of the world is that that these guys are cold mercenary people, and the only thing that matters is money, and that they expect a certain return on their money.
Budget.
And so I would guess, if I had to make a single principled model, I would say the gross of a movie is going to be some percentage. There's going to be some constant of all the money that the gross that goes back as profit. But it's basically going to be something like the expenses for the movie, the budget for the movie, plus I need to make some kind of a profit margin, let's say 20%. So my guess is going to be that that's not really a real formula, but I would argue that the gross is probably going to be something like what the budget is, and then expect that I'm going to be getting 20% profit, because that's what I assume what the movie guys want to make. Okay, and that would be one kind of first principled way model for it. Okay. A data-driven model is probably more like what you guys are doing, okay? Which is that you're looking at a bunch of features and trying to see what correlates with it, okay? Any questions about that? Okay, there's either a theory of the world underlying it, or there is a data thing underlying it. And again, ideally, you will have some kind of element of both. While I'm at it, any questions about that homework 3 problem? Any questions about homework 3 now that I got a few more people on here that people want to discuss? Nobody. Okay. Now, an important thing which in any modeling effort that that I think it's important to do is to build to see how good your model is. It's very, very important to be able to compare it against a baseline. Okay? A baseline, in my mind, is a simple, not stupid, but a simple model. Okay? Based on kind of what you know about the world, based upon what you know about modeling. And you know, basically, this gives you, sometimes the baseline models are very good. Okay, I recall a discussion on the last homework where somebody said, oh my God, that a really good model was just how many sales did this item have a week ago? Okay. So what are examples of baseline models? Okay. There are a lot of sort of ideas for baseline models that are different in what you call it on different kinds of problems. One, if let's say you were doing classification, might be to select the labels, okay, at random, maybe based according to their frequency. Suppose you're trying to predict, you know, if it's a car or a truck. How many cars do you have? How many trucks do you have? Okay. If in your training data, there are a lot more cars than trucks, maybe a good model to pick is to take the majority label. Okay. If I knew that there were more cars than trucks, what if I say everything is a car? Okay. That's a reasonable baseline model. Okay. A simple model, especially for, let's say, another simple baseline model might be a single variable model. The student who said, oh, what about popularity? The gross should be a function of the popularity. She is sort of suggesting a one variable model. Okay, gross is a function of popularity. And that seems like a perfectly reasonable model. Okay. Another model is what was the same label or value at a previous point in time. That's what did very well on the, the sales data problem. Okay. There might be other heuristics. Like I told you, I gave you my budget model, which says that the gross should be enough to turn the guy a decent profit, or else they wouldn't be making these movies. And again, a baseline model, in my mind, it's got to be fair. It's got to use data that you actually have, okay? And it should be simple, but ideally you would have a bunch of them and not all of them are stupid, okay? So that to see whether or not you're really doing something interesting in your modeling. Any questions about baseline models? Actually, let's come back here. What would be a good baseline model in your movie gross thing? I didn't ask you for this thing now. But what would be reasonable baseline models for movie gross things? If you want to predict how a movie is going to gross, what might be a reasonable thing to try to do? Simple, not really, just rule of thumb things. Any ideas?
You could find a simple correspondence between budget and revenue, just like a multiplicative factor for the average budget to the average revenue. Just apply that.
That's budget to revenue. So that's kind of an argument that's basically like, what is the profit that they expect, right? So you're proposing a one variable thing between budget and revenue. That seems like a reasonable baseline model. Okay. What about something, other models that one might think about? What else would be a simple baseline model? What about the average that a movie grossed last year? Okay. I don't even have to look at the details of my movie. If I know what movies are, if I know that the average movie grosses $10 million a year, one prediction is to say this movie is going to gross $10 million. Okay. Any other kind of baseline models that one might think about with movies? Okay. Again, in this case, I think that we talk about the temporal one. We looked at the most common label. Okay. These seem like reasonable things. Any questions about that? I do think setting up baselines is a very good thing for any modeling effort. And the final, I think, thing that if we want to be consistent with Nate Silver's view of the world was to update our predictions over time using something like Bayesian reasoning. What was Bayes' theorem? Okay, which we've mentioned a couple of times. Bayes' theorem tells us what is the probability of A given B, where it's the probability, if we knew what the probability of A was, okay, let's say that let's interpret Bayes' theorem as saying, what is the probability of event A happening? Let's say Trump winning the election as a function of B, let's say today's polls. What would be the Bayesian interpretation of it? Well, we had some probability that Trump was going to win based on what we had already sort of seen. And then we're going to be adjusting it by basically what is the probability that we saw the new polls given what we knew before. Okay? If the polls before are fairly consistent with what we had seen before, that's not going to change the probability a lot, okay? Divided by what was the probability we saw these polls, okay? So, again, these things are, there's this notion of, basically we're updating the posterior probability, what happened afterwards, according to the original prior probability, okay, based on the likelihood, okay, and the marginal probability. In principle, it should be clear that Bayes' theorem is gives us a technique for sensibly updating forecasts in terms of new information. These may be hard things to estimate, but if we can estimate these things, we can now figure out what the consequence of these things are. Any questions? Okay, good. And again, I do think that developing baselines, okay, simple baseline models is a good habit to be done. Again, we discussed movie gross. What would be if you wanted to try to predict what the weight of a baby is going to be? That was one of our prediction challenges. What would be a reasonable baseline model to predict what somebody's baby is going to weigh?
if they've had previous babies, maybe just give it the same number?
They've had previous babies, you're saying, oh, so one model is, did they have a previous baby? And if so, the same one's going to be, it's going to be the same thing. Maybe that's a more specific thing. I'd like to think of a simple baseline.
Average weight of
I would think average birth weight is a great thing, okay? Without the absence of any other information, the average, would be good. Ideally, the average in a representative cohort. So, the data differ by state? Does it differ by something like that? What were other reasonable, what would be the reasonable, if you had to get an expected price for what was a piece of art going to sell for at auction? What would be a reasonable baseline model for that?
average price for the artist, like whoever.
What might be if you're selling a Picasso painting? What was the average Picasso painting sold for? That's one. Another one was, how much did this piece of art sell for before? Okay, if they have records on how much this painting sold over time, that would probably be a pretty good clue. Okay. Anyway, I think you should get the idea that kind of developing these simple models is kind of an important prerequisite. Okay, to seeing how impressive your results are. Okay. What is a reasonable model to predict whether chances are of it snowing on Christmas? What would be a good baseline model at this Christmas? What's the chance we're going to get snow here in Long Island?
Just the probability over the last 50 years that it snowed.
Maybe it would be the probability over the last 50 years. Okay. Maybe over a shorter period. Again, I think that, with global warming and stuff like that, one might have a different idea, right? Anyway, learning to think in terms of simple baseline models that are not these complicated machine learning things is good for keeping you honest, okay? And that I think I encourage. Any questions? Okay, the last thing I'd like to talk about today is just some other, let's say, character. If you have to build some kind of a taxonomy of models, there's different modeling techniques that people use. There's questions of linear versus nonlinear models, okay? And we talked about that a little bit with bias, these kind of bias variance trade-offs. Linear models tend to be simple, but they don't capture a certain phenomenon that is nonlinear, okay? And, that's one thing to be aware of what you're doing. Are you building a discrete model or a continuous model? If you're doing linear regression, you are presumably building a continuous model. You have real numbers coming in and a real number coming out. Some models are discrete. Things like simulations, Monte Carlo simulations tend to be discrete events, okay? Whether you're building something that is kind of a complete black box, and again, machine learning models tend to be, deep learning models tend to be black box models, versus a model that's giving you some kind of a description of why it's making its decision. Okay, so there are a bunch of different criteria that that you should be aware of what your model is doing. When I think about discrete versus continuous, okay, again, I think about Monte Carlo simulations are an example of discrete events, okay? If you wanted to predict the results of an American football game, you could use something like some kind of continuous function to predict what the score of a team is. Or you could try to simulate games and see what happens. How much do they gain on each play and what happens on each play? And if you play 1 million games, maybe you will end up doing, finding the, a probability distribution that's interesting. there's kind of this notion again of which I think I've kind of hinted at before. When I think about machine learning models, a machine learning model like a linear regression model is a very general model. It is it doesn't use anything that is related to the difference of the problem. Doing linear regression fitting, it's the same model, whether you're using it to predict movie gross or sales or anything like that. There are other models that are kind of based more on what you know about a domain, okay? And I think that's kind of an important thing to know. Often, again, in machine learning, you guys are all taught to use, general machine learning models, okay? I encourage you not to be too afraid of what you call it, of using what you know about the world. So what are the final things I want to say about modeling today? Okay, one thing that's important is it's important to develop reasonable baselines. It's important to try to see if there's a way to think about your models in terms of probability distributions, so you get a range of forecasts. And it's important to kind of test them with data that is kind of moving. Because one thing that, and we'll talk next class, will be about kind of evaluating models. But understanding that I get more impressed with models that make forecasts in the future, and the future forecasts are true, than ones that get high p-value, high accuracy values. Okay, based on data that you've already had to cook and you kind of knew about at the time that you were building the model. But we'll talk about evaluation next time. Any questions?